Okay, I think we'll get started. Quick review of what we have done before. We have talked about dielectric interfaces, and we have talked about different polarization configurations. So, the case where the E field is perpendicular to the plane of incidence is known as the perpendicular polarization, and the case where the magnetic field is perpendicular to the plane of incidence is known as the parallel polarization. And we have seen how to write the incident, transmitted, reflected wave expressions. Okay. We found that for both the polarizations, the form of the expressions for the E field and the H field were identical. Okay. The details are definitely different. The reason why the details relating to the transmission and reflection coefficients are different are simply because the boundary conditions are different for different polarizations. In one case where the electric field was out of the plane of incidence, everything was tangential. So, Ei plus Er was equal to Et, right. But for the other case, we had Ei cos theta I minus Er cos theta I is equal to Et cos theta T. So, the magnetic field boundary condition is also different for both polarizations, and because of this we could get the values, or we could get the expressions for the reflection and transmission coefficient for the two polarizations. There are subtle differences between the two. For the perpendicular polarization, when we talk about electric field reflection coefficient, 1 plus gamma is gamma perpendicular is equal to tau perpendicular, but for the parallel polarization case, 1 plus gamma parallel is not equal to tau parallel. You will have to use some other expression. Okay. We also saw that in order to make the reflection coefficient 0 in both the polarizations, there is a possibility of using different incident angles for a given material configuration. All right. So, the general form is, for the perpendicular polarization, for the perpendicular polarization, you will have cos inverse of eta 1 by eta 2 cos theta t. All right. And for the parallel polarization, eta 2 by eta 1 cos theta t. So, it is just reversal of the intrinsic impedances. You remember this much, and if you are able to calculate cos theta t from the given problem, then you could calculate the Brewster's angle in no time, right. But the Brewster's angle for different polarization is different. That means that in order for you to get a reflection coefficient 0, all right, you have to understand that it would be possible only for one polarization, all right. And for the other polarization, that angle of incidence where you get 0 reflection is going to be different. So, impedance matching or having no reflections in electromagnetic waves with arbitrary polarizations is not easy, unlike transmission lines, okay, and it requires tremendous effort. And we also saw that in general cases, all right, the Brewster's angle expression was that, right. However, one could say that majority of the materials are non-magnetic, all right. If that is the case, you could substitute for mu1, mu2 as mu0, and then you will observe that for the perpendicular polarization, the case for Brewster's angle is not easy to get, all right. And in fact, in the case of non-magnetic material, there does not exist a Brewster's angle for perpendicular polarization. However, for the parallel polarization, you do have a real angle that you are getting, all right. That is a detail, all right, but the most generic form is what we saw before, right, cos inverse of eta 1 by eta 2 cos theta t. Okay. Now, we have to proceed and patch up a few things, okay, with respect to our understanding. The first and foremost thing that we can do is look at the reflection and transmission coefficient expressions. The simplest thing one can do with, say, perpendicular polarization, right, is take the expression for the gamma perpendicular, substitute incident angle theta I to be equal to 0. Okay. If you have incident angle to be equal to 0, then it becomes normal incidence on the second medium, right, which also means that the transmitted angle has to be equal to 0. So, cos theta I and cos theta t will both be equal to 1, and then you will end up getting eta 2 minus eta 1 by eta 2 plus eta 1. This is a sanity check to see whether our expression is holding good for normal incidence. So, for normal incidence, we already know that it should be eta 2 minus eta 1 by eta 2 plus eta 1. This is the case for gamma perpendicular. Let us look at gamma parallel, right. if you substitute cos theta I equal to 1, cos theta t equal to 1, you get eta 1 minus eta 2 divided by eta 1 plus eta 2. Immediately we have to notice that gamma perpendicular and gamma parallel do not seem to be the same at normal incidence for the two polarizations, alright. So, casually if you substitute theta I and theta t to be equal to 0 degrees, you will notice that gamma perpendicular is negative of gamma parallel, alright. Now, this raises some confusion, alright. Why is it that in one case the reflection coefficient is negative of the other? The simple interpretation that we have to look is, it is not the problem with the reflection coefficient calculation, it is the way we have set up the problem itself, alright. So, if you go back to the diagrams that we have drawn, you have to understand that in the first case we made a very clear assertion that the electric field directions do not flip, alright. So, the incident electric field was pointing out of plane, the reflected electric field is also pointing out of plane, the transmitted electric field is also pointing out of plane, and all of them are oriented out of plane in the same direction. So, we made an assertion that the fields do not flip the sign as far as E field is concerned. But the way we have drawn the right hand side figure, we have said that the E field will flip its direction. Okay. So, we have made the assertion that the E field is going to flip its direction in response to the change in the K, alright. So, the reason why that sign change is coming in is not because of some arbitrariness in the setup, it is because we have made the electric field flip its direction in the parallel polarization case, right. So, there is a difference, but this should not be looked into very seriously, alright. For normal incidence, the reflection coefficient is eta 2 minus eta 1 by eta 2 plus eta 1, okay. Now, suppose you have your setup in such a way that you have managed to flip the direction of electric field while doing the analysis, then you will end up with a minus sign, okay. So, this is some tiny thing that you will have to keep in mind. If you directly substitute, you may get a difference of one minus 1 sign between the two reflection coefficients. So, you have to be a little careful in interpreting that, okay. The other thing is, let us go a little bit further and build on these two, right. Let us take the Snell's law, okay, and so far in order to calculate theta t, we have used Snell's law, okay, n1 sin theta I is equal to n2 sin theta t, okay. So, we will start with Snell's law, n1 sin theta t. You could also write this down in different way. I mean, we already did this before, alright. You could also use betas, there is no issue. Beta 1 is 2 pi divided by lambda naught divided by n1, and beta 2 is 2 pi divided by lambda naught over n2. You could also write this down as beta 1 sin theta I is equal to beta 2 sin theta t, both are Snell's law, okay. And one of the things that we have done in all the prior derivations is that we have used wherever we had sin theta t or cos theta t in our reflection coefficient calculations, we had cos theta t coming into the picture. Whenever we had some cos theta t, we tried to substitute it in terms of theta I to reduce the number of variables, right. So, we could say that sin theta t is beta 1 by beta 2 sin theta I, okay. Okay. So, sin theta t is beta 1 by beta 2 sin theta I, okay. Now, is it possible for theta t to be equal to pi by 2, or is it possible for sin theta t to be greater than 1, consequently cos theta t to become imaginary, alright. So, we have to see that particular condition, alright. Now, if you tune your incident angle to be in such a way that sin theta t is equal to 1. So, the left hand side is equal to 1. That angle of incidence is known as the critical angle for a given material interface system. Okay. So, if sin theta t becomes equal to 1, with indices n1 and n2, all right, at a specific angle of incidence okay, that angle of incidence is called critical angle. Okay. Okay. So, this also implies that theta t, right, at theta I equal to theta c is pi by 2 or 90 degrees with respect to the normal. You could also have, for example, theta I to be greater than this angle, all right, and you would still notice that your theta t becomes very tough to define, right, and you know, you have to look at what happens to the transmission and reflection coefficients in these cases. Okay. And one of the things that we could do is look at this specifically with respect to our expressions for the gamma and tau that we have got in the previous case for the two polarization. We can look at just the reflection coefficients and try to make some inferences as to what is happening, right. So, we had gamma parallel and gamma perpendicular. Okay. Now, we know that this angle is the critical angle, all right. You could also have incident angle to be higher than that, right, going all the way to the pi by 2 at the input itself, okay, which means that at angles higher than this critical angle, okay, sin theta t is going to appear to be greater than 1, okay, or in other terms beta 1 by beta 2 sin theta I okay. These are the specific cases that we are saying. First thing that we have to determine is whether this is going to be possible. Okay. So, beta 1 it will be given as omega square root of mu 1 epsilon 1. Okay. So, I can write this down as omega square root mu 1 epsilon 1 divided by omega square root mu 2 epsilon 2 sin theta I greater than equal to 1. Is it possible? Right. So, then we can say that sin theta I, in order to preserve this inequality, is greater than equal to square root mu 2 epsilon 2 okay. So, I have sin theta I greater than equal to square root mu 2 epsilon 2 by mu 1 epsilon 1. Okay. Okay. Now, let us look at this right hand side term a little bit more closely. Let us say that in order to make my analysis a little simpler, okay, in order to make my analysis a little simpler, I can always say that the media I am considering are non-magnetic media. So, I can substitute mu 1 equal to mu 2 equal to 0. Okay. You can substitute mu 1 equal to mu 2 is equal to 0, mu naught, all right. So, I just end up with mu naught getting cancelled on the numerator and denominator, and I have square root of epsilon 2 by epsilon 1, right. So, I just need to have okay. Okay. So, as far as the incident angle goes, we have control. When you are doing the experiment, you have control over the incident angle. Let us assume that you have control over the incident angle. You can go from 0 degrees to 90 degrees. That is how you will rotate your incident beam with respect to the interface, all right. There is no way for you to make your theta I greater than 90 degrees, all right. So, this means that the left hand side of this inequality does have a limit, it has to be less than 1. Okay. So, if the left hand side has to be less than 1, all right, then we have some conditions coming on the right hand side. Okay. This means that your right hand side also has to be less than 1, all right. So, you can say that okay. I am not going to make it equal to 1. Equal to 1 means that you are just having the same material on two sides, the interface no longer exists. So, the only case where you have two different media and the interface still exists is not having that equality over there. So, square root of epsilon 2 by epsilon 1 has to be less than 1, which means that square root of epsilon 2 has to be less than square root of epsilon 1. So, if this condition is satisfied, right, if you have two media, the first medium is having higher permittivity, the second medium is having lower permittivity, then there is a chance that you are going to be ending up with theta t, okay, not being clearly defined, that is sin theta t will look like it is greater than 1 according to the Snell's law. We already know that if sin theta t looks like it is going to be greater than 1 according to Snell's law, if you try to calculate cos theta t using 1 minus square root of 1 minus sin square theta, you are going to get a pure imaginary number. You are not going to be able to determine what is the angle of transmission in these cases. Okay. So, first we have established that it is possible to have sin theta t to be greater than 1 just using simple Snell's law. The way to achieve that is by using your second medium to be rarer than your first medium, and there does exist an angle where your sin theta t will go greater than 1 and cos theta t will become purely imaginary. So, that possibility still exists. Okay. So, it is not an impractical case where we are saying that theta t will become pi by 2 and sin theta t will become greater than 1. So, according to these expressions it is possible, but what does that physically mean? Something that we have to see. Okay. So, if this is the case, we have to go back to our expressions for gamma. Okay. So, I am going to just go back to our expressions for gamma. So, I had gamma parallel, okay, I just go and copy and paste this expression. Okay. So, I have gamma parallel is equal to eta 1 cos theta I minus eta 2 cos theta t divided by eta 1 cos theta I plus eta 2 cos theta t. This is the expression that I have from the previous class. Okay. And I want to take the scenario where the sin theta t is precisely equal to 1. I will start from there and then I will try to figure out what will happen if sin theta t becomes greater than 1. So, at precisely when sin theta t is equal to 1, we call the incident angle to be critical angle, all right. So, if sin theta t is equal to 1 and it becomes greater for higher angles of incidence, then writing down cos theta t becomes a difficulty over here. Right. So, what one can do is sin theta c, just to remember, is beta 2 divided by beta 1 or n2 divided by n1, right. And if this quantity becomes, if you have incident angles to be higher than this angle, then you are going to be having some theta t, which is not going to be possible for you to get real angles with cos, right. So, if this is the case, what can we do with respect to writing the angles inside? So, we keep eta 1 cos theta I as it is, okay, and then we look at the second term, eta 2 is also okay. You can always write down the angle here to look like 1 minus okay. So, what I am trying to do is I am going to try to replace theta t in terms of theta I, okay, and I am just using Snell's law to do that. Okay. So, once again the denominator I have eta 1 cos theta I plus eta 2 cos theta t, once again it is 1 minus beta 1 square by beta 2 square sin square theta I. Okay. So, to be more precise, the square root that we are having over here, right, this is going to give you some negative number, right. So, you are not going to be able to determine the cosine very easily, because the root of that will become j, right. So, if you want, you could also do one thing, you could multiply these terms with minus 1 and take a minus 1 out, because we know that beta 1 square by beta 2 square sin square theta I is greater than equal to 1 for the condition that we are already considering. You could always reverse the numerator, alright, and the denominator and take a minus 1 outside. So, you could just write down these terms as eta 1 cos theta I minus j times eta 2 square root beta 1 square by beta 2 square sin square theta I minus 1. You could just write it down like this, right, so that the term inside your square root is positive, okay, but you did bring a j outside, divided by eta 1 cos theta I plus j times eta 2 square root beta 1 square by beta 2 square sin square theta I minus 1. There is a reason for doing this, alright, and the reason is because I want to make some inferences from the value that I would ascertain, which is coming from here, alright. One of the things that I know now clearly looking at this is, to make this expression a little simple, I could say that let eta 1 cos theta I be given a variable name x, okay. Let eta 2 square root beta 1 square by beta 2 square sin square theta I minus 1, right, be given the variable name y. Then I can write this formula in a much simpler way, okay. So, the formula would now look like x minus j times y divided by x plus jy, okay. So, the reason for bringing that minus 1 out and then writing it in terms of j is to write it in a form of ratio of two complex numbers that are conjugates of each other, okay. And there is a reason to do this again. I know that the magnitude of the complex number is given by square root of x square plus y square. The magnitude or the absolute value of the complex number of its conjugate is also square root of x square plus y square. So, it is clear to me that this is a ratio of two complex numbers of same magnitude, okay. So, I can say that this ratio as far as magnitude goes is equal to 1, okay. So, this is the purpose for rewriting it in the flip form and taking j outside, so that I can make this assertion that magnitude of gamma parallel the way we have written, is equal to 1. Okay. Once I have determined that magnitude of gamma parallel is equal to 1, I know that no electromagnetic wave is being transmitted, all of it is being reflected, alright. So, now I can say that at the interface between the two media, when I have a denser medium followed by a rarer medium, if I adjust my incident angle in such a way that sin theta t is equal to 1 or higher, alright, what I would end up getting is magnitude of the gamma to be equal to 1, alright. Notice that I have written clearly magnitude of gamma parallel is equal to 1, I am not talking anything about its phase, but all I know is whatever I am sending in is going to be reflected from the interface, right. So, this is true for all angles where cos theta t is imaginary, which means that all angles where theta I is greater than theta c, your magnitude of your reflection coefficient is going to remain 1. Okay. So, the angles at which this happen correspond to a scenario which is known as total internal reflection. So, in short form they people make it look like TIR, right. Total internal reflection is the phenomenon where you launch an electromagnetic wave from a denser medium to a rarer medium, and you have your incident angle to be greater than equal to critical angle, then you will notice that in your reflection and transmission coefficients for different polarization, you will notice that the reflection coefficient becomes equal to 1, at least for the parallel polarization, that is what we have seen. For the perpendicular polarization also, it becomes, the magnitude becomes equal to 1, right. So, let me just complete this by saying also irrespective of the polarization that you are using, okay, the entire electric field is going to be reflected, there is nothing you can do about it. Okay. So, the interface between a dielectric and another dielectric could act as a perfect reflector, okay, and the question can be what is the angle of reflection? We already know that the angle of reflection is going to be equal to the angle of incidence, right. So, that is something to remember. Right. So, now that you know what is this total internal reflection and it is possible, there are two extreme conditions we have seen. In the previous class, we saw the conditions where gamma is equal to 0. Gamma equal to 0 was known as the Brewster's angle. And in this class, we are seeing the extreme opposite where gamma is equal to 1, alright. This is known as TIR, alright. And generally the wave propagation where you have transmitted, reflected is in between these two. Okay. So, you have seen the two extremes and you can have anything in between the two. So, you can have reflection coefficient going between 0 and 1, right, that is it, right. So, those are the boundaries of what you can see, but there is only one more detail that we will have to see. Okay. Just like we have seen the two extremes with respect to the reflection coefficient, we also have to understand the way we have formulated the problem. We have also seen two extremes, that is electric field is either completely perpendicular to the plane or it is completely lying in the plane of incidence. Those are also two extremes, alright. In reality, you may have polarizations where electric field has a component that is parallel, has a component that is perpendicular to the interface. In all these conditions, you will have to break the electric field into two components. You have to project the electric field to the plane, take the component of the electric field along the plane, and then you will have to project it perpendicular to the plane, take a component perpendicular to the plane. You may have to calculate gamma parallel, gamma perpendicular for the single case, and then we know that the electric fields overlap and it can be superposed, alright. It follows the theory of superposition, it is a linear term, you can add electric fields in a quantity. So, that means that you will start taking gamma parallel, gamma perpendicular, etc., and then calculating the reflected electric field for both these polarizations, and then you will be adding them up together to get the net electric field that is being reflected. Okay. So, that is one thing that we have to remember. In many of the problems, you may have some polarization which is neither parallel nor perpendicular. In those cases, you will have to project your electric field into the plane, take the in field component and then out of plane and take the out of plane component, and then you will have to find out gamma parallel, gamma perpendicular. So, in a given problem you may end up using both the polarizations to figure out what is the net effect. In doing that, we can immediately say that if that is the case, and if we look at the expressions that we have, we already know that gamma perpendicular and gamma parallel are not equal, right. They are not equal, they are different, which means that you could have different gamma perpendicular, gamma parallel, right. So, you have to be very accurate in the calculations that you make and also the inferences that you will make. Okay. So, let us say take some conditions and let us start to look at what are going to happen. Okay. The first thing that we will do is we will say that any electric field okay, with respect to this plane of incidence can be divided into EI parallel and it can be divided into some EI perpendicular. Now, in the case of EM waves, when we had begun this and we were talking about the differences between the EM waves and the transmission lines, we were talking about polarization, and then we talked about linear polarization, circular polarization and elliptical polarization. Okay. In those lectures, okay, one of the things that we were noticing was you could have Ex and Ey, okay, they could have different values or they could have different magnitudes, and there could also be a phase difference between Ex and Ey. We also saw this using an animation later on, alright. So, you will be having Ex going this way, Ey going the other way, but they need not be in phase, alright. However, if they are in phase and if their values are different, then you will end up having a linear polarized light. So, let us take our current scenario where we have calculated all these reflection coefficients. Let us say that the incident light is linearly polarized. Okay. Immediately the question comes, we have written EI is equal to EI parallel plus EI perpendicular. Should we also be more generic and say that EI perpendicular and EI parallel can have a phase difference between them, just like Ex and Ey could have phase difference between them in the simulations that we saw before. Here also it is quite possible that you can have a phase difference between them generally, okay. But if you are talking about linearly polarized light, then we are talking about this phi becoming equal to 0, then it becomes a specific case where EI is equal to EI parallel plus EI perpendicular and you do not have any phase difference between EI parallel and EI perpendicular. Okay. So, if it is linearly polarized, just make phi equal to 0, okay. You will be having EI is equal to EI parallel plus EI perpendicular, then you will take the EI parallel component, you will be doing the calculations for the reflection coefficient, you will be taking the EI perpendicular component and you will be calculating the reflection coefficient. In both these cases, you will be able to calculate the reflected wave ER, and then once you get ER parallel, ER perpendicular, you will just add the two to get the net reflected electric field in medium number 1. Okay. So, this is the procedure if you had a linearly polarized wave. Now, while doing this, there are other things that we have to consider. Okay. If you look at the expressions of transmission and reflection coefficients that we are having, these are real numbers. Okay. Gamma perpendicular, gamma parallel are all real numbers. There is no need for them to be complex. Okay. So, if this is the case, for a linearly polarized wave to go and hit the interface and then bounce back, alright, there will not be any arbitrary phase imparted to your incident wave, right. It is good because your reflection coefficients are real, right, which means that you will not have any changes in phase coming out of this. So, if your incident electric field was linearly polarized and if you split that into parallel and perpendicular components, each of them is going to be having a reflection coefficient that is real, all right, and then you add them together, right, you will end up with no manipulation of phase between them. So, you will not be giving only parallel polarization some phase, perpendicular polarization no phase, and all that will not happen, they will still remain in phase. Okay. So, which means that EI parallel, EI perpendicular in the case of linearly polarized wave will lead to ER parallel, ER perpendicular with no phase. So, if you have to add them up together, you will immediately realize that ER is also going to be linearly polarized, but ER parallel value is not the same as ER perpendicular value, that is the reflection coefficients are not identical. So, the linearly polarized wave could undergo a change in angle at which it is polarized simply because the y component or the perpendicular component is different from the parallel component. That is all, but it will remain linearly polarized. So, a linearly polarized wave hitting the interface, the transmitted light will be linearly polarized, reflected wave will also be linearly polarized. However, the angle at which it is polarized could change simply because the reflection coefficients and the transmission coefficients for the both polarizations are not identical. So, it will stretch one component more than the other. Okay. So, linearly polarized wave will remain linearly polarized in this material system. Right. So, reflected wave linearly polarized, transmitted wave is also linearly polarized, right. So, then we can take another scenario, if your incident wave is circularly polarized. Okay. So, for a circularly polarized wave, in the prior lectures we had seen that mod Ex was equal to mod Ey and a phase difference of plus pi by 2 or minus pi by 2 was present between these two. If it was plus pi by 2, you would have one handed circular polarization, maybe it is right or left, right, and if it is the opposite minus pi by 2, you will be having the opposite evolution of polarization, or we call it left, or it is the opposite, one is right handed, another one is left hand circular polarization. So, here we can say that equivalently here your EI parallel right is the same as your EI perpendicular magnitude, that is how you define circularly polarized with respect to an interface, and there is a phase difference between the two, and it could be either plus pi by 2 or minus pi by 2 depending upon whether you are having left or right circular polarized wave. So, this would be the condition for having circularly polarized wave hitting your media interface. Okay. Now, once again we know that the reflection and the transmission coefficients are real. Okay. So, they do not change the phase, they just change the values of your reflected and transmitted waves peak. Okay. They do not change any arbitrary phase between these two components, which means that the reflected and the transmitted waves are going to exhibit the same phase difference between the two components, right. So, for the reflected case, your phi will still remain at plus minus pi by 2. For the transmitted case, phi is equal to plus or minus pi by 2. Okay. Now, we also know on top of that, just like in the linearly polarized case, gamma parallel is not equal to gamma perpendicular, reflection coefficient values are not equal, which means that whether if you had EI parallel and EI perpendicular to be equal, ER parallel and ER perpendicular may not be equal. So, what happens is you will end up with ER parallel not being equal to ER perpendicular, but they still have a phase of pi by 2 between them, and this corresponds to an elliptical polarization. Okay. The same thing happens in the case of transmitted wave. The transmission coefficients are not equal. Okay. So, which means that your ET parallel need not be equal to ET perpendicular, once again becomes elliptical. Okay. Now, there is also another tiny detail that you will still have to remember. We have said that ER parallel is not equal to ER perpendicular. That generally means elliptical. It is also possible that one of them is 0, because you have a case where you have Brewster's angle occurring in one polarization, all right, where you have gamma equal to 0 for that polarization, but in a normal non-magnetic material gamma for the other polarization is not 0. So, it is perfectly possible that you get only one polarized component, the other polarized component is not present in the reflected case. So, it is perfectly possible that your input was circularly polarized and the reflected is only linearly polarized. Okay. So, there are cases where multiple things can happen, but one thing is for sure, you cannot have reflected and transmitted to be circular. The most generic case, they look like elliptical, but it is possible that this elliptical gets down to being linear in one of these components. So, the circularly polarized light, there are many things. You will have to look at the media interfaces, calculate the coefficients and calculate the values of the reflected fields, and then you have to decide what the polarization is going to be. But in general, it has to be elliptical. It could become linear under certain conditions depending upon your value of gamma parallel and gamma perpendicular. Okay. So, this is the thing. So, what have we seen now? We have seen that the magnitude of the electric field is changing upon reflection and transmission. We have also seen that the polarization of your EM wave is changing depending upon your medium configuration. The only thing that we are certain is there is no arbitrary phase change between components, because your gamma and tau are actually real numbers. So, these are the things that we have seen, and we have also seen some extremes. Brewster's angle corresponds to gamma is equal to 0, and we have also seen the opposite case, which is total internal reflection, where gamma is equal to 1. Okay. So, anything is possible using dielectric interface, and we also know that if you make the angle of incidence to be equal to 0, you will get reflection coefficients to look like transmission line reflection coefficients. However, here you have two polarizations, and in the way you have constructed the problem, you have flipped the electric field. So, one polarization will have negative reflection coefficient of the other. So, you have to be careful in interpreting these things, right. With this, most of the topics related to dielectric interfaces are over. Okay. The only thing that we need to start looking at is dielectric metal or dielectric conductor interfaces, all right, and then we will have to see how to make use of these things in some settings to send guided light, etc. But before that, what I want to do is I want to go back to the programming part, because it has been a while we did some programming. Okay. I want to take a couple of these things and just show you what is a plane wave, all right. By solving Maxwell's equations, we have seen only graphs. We have not actually seen a wave that is bound in two spatial dimensions. We have seen only in one spatial dimension. So, in the next class, I want you to bring your computer again with Octave. We will take the simplest case where we have del cross E, del cross H, but instead of having E in x direction, H in y direction and all that, we will try to see whether we can make two-dimensional analysis. That is, we will try to see what is a point source, what is a spherical wavefront, what is a plane wavefront, etc., and get a more visual feeling. This part of the simulations will be slow, okay, because it has the matrix sizes will become where it was 100, now it will be 100 by 100. Okay. So, it will be slow, but we will do some portions in class, some portions I will ask you to do for your own information. back home, okay, because it is slow, right. So that's the only thing. So next class I request you to bring your computers with Octave loaded. We will go over some visualization for these plane waves, possibly total internal reflection or Brewster's angle also, okay. So we'll stop here.